So welcome today, including today, there are 300 days left in 2026. And what a better way to start it than in Science Circle. So I'm going to begin. I hope you've enjoyed the opening slide. And first off, one thing about it, you think about beryl or how beryllium was in the hands of humans. I thought it was interesting to consider the idea that it relates to a sense of magic. In the lower left-hand corner here in this slide are magical gemstones that are on display in a collection in a museum in Liverpool. And there's many one could show. I showed fake replicas of Superman's crystals that are sold on eBay or Amazon or somewhere. There just to show how fascinated people are with crystals, and there's all this subculture about crystals. And they're beautiful, and they fascinate. They fascinate crows and other animals that have pattern recognition as well, with capture of color and refraction and reflection of light in interesting ways. So our earliest history for the longest time seemed to be in terms of, look at this beautiful stone, and this must be valuable. And culturally, it's still in our veins because you see it's used in cinema. So beryl is the first form that was known that was found to contain beryllium. It's a beryllium aluminum silicate. This maybe someone changed my slide. Beryllium aluminum silicate mineral, and there's another form of beryllium ore that somebody's clicking on my thing here, please. That doesn't have the aluminum. So in terms of the jewels that you think of, the crystals, aluminum is one of the big aspects that makes the crystal a beryl. They're very hard, hexagonal crystals. And we have, let's see, this is slide 4. I'm going to just show you forms of beryl quickly. Bixbyite, which is better called red beryl. It has trivalent manganese, substituting for atoms of aluminum in the structure. And heliodor, which has a yellow quality because of iron impurities, specifically ferric iron. Ik is greater than us. Ferric is +3 valence, and ferrous is +2, just so maybe jog somebody's memory out there. So these various other elements in small amounts can impart striking differences in these crystals. The third and fourth forms are morganite, which has pinkness due to trivalent manganese, and you have a upper left sample of that. Aquamarine is blue-green due to ferrous, Fe+2 iron impurities. And so sometimes impurities can make for pretty cool outcomes. I have in my PDF more description than I'm going to take time to read, but I just wanted to show these. And the Phil Youngblood's favorite, apparently, because I saw him mentioning this, is emerald, which is green because of trace amounts of chromium, which is element 24, and sometimes vanadium and let's see, 23, I think. Vanadium's 23, next to chromium in the periodic table. Um, I always think scandium, titanium, vanadium. Um, so that's what you get with these crystalline structures with aluminum and silicates and beryllium and traces of other elements. This is the guy, Volkelin, I guess, is the best I know how to pronounce his name. So Louis, I'm going to call him. He was kind of like this. He was. I kind of looked into this because I wondered how he happened to manage to survive the Reign of Terror when Lavoisier got whacked and wasted by the tyranny. And he was a farm boy from Normandy and worked in an apothecary and worked his way up in the halls of intelligentsia, so to speak. And he discovered two elements, chromium in 1787 from studying a mineral sample from Siberia, and beryllium in 1798. And I thought it was interesting. I won't go over this in detail. I put it here so that people, when they have the PDF in hand, can look at this if they want to. How would you in 1798 process a stone to figure out what it was? And it was a time when true chemistry was emerging from the traditions of alchemy, and certain things were expected, and it was very empirical. There was a lot of rudimentary theory, but they managed their way through. And so I'll let you read how he figured it out. But he was not able to isolate the pure beryllium metal. That was done in 1828, which is 1 year after Ludwig van Beethoven died, just to kind of put it in a time scale for you. By the way, that little picture there in the center, just below Balaquin, is Napoleon in 1798. I think it's from 1798. And he was taking advantage of the power vacuum, working his way in. So 1828, other scientists managed to isolate pure beryllium metal. Well, of course, they didn't have much. Beryllium's pretty rare. And just for the words people out there, beryl comes from Greek for pale green, I guess, and there are references to beryl in many old texts, including Revelations and other places in the Bible, the New Testament of the Bible, and I thought this really showed all the more how people regarded precious stones as something that fell in the context of the divine and more of that magical thinking to my thought. One of the things that was first called glucinium because it had a sweet taste, but that was changed by Martin Heinrich Klaproth, who was a very productive chemist in Germany. And he changed the name to beryllium for this new material, this new stuff, to emphasize its source from the mineral beryl. And a lot of stuff was going on. This is a flash slide just to kind of point out discoveries, electricity and magnetism. It was only 1825 that the electromagnet was invented by um, several people came on it, but this Sturgeon uh, uh, discovered uh, electromagnetism, and um, uh, Joseph Henry invented a electromagnet with a relay, and relays really became one of the early cornerstones of information technology, hard structure, infrastructure. That's one reason I wanted to mention it. Uh, Now, jump forward a bit to 1883. Uh, just a few things going on, Franco-Prussian War and that sort of thing. But there was a mineralogist, Emil Bertrand, who must have had extraordinary pattern recognition and attention to detail, and probably was uh, uh, kind of a hoarder. I bet his keeping straight all the stuff he collected. He was a collector, and I make a point of that on the later slide here. But he discovered a mineral called Bertrandite, which was named after him, which has become pretty important, but it was very hard to find. He found one little bit near mine in France, and it took a few years before another bit of it could be found. And after 3 years, chemical analysis of it was performed. So it became recognized as another source of beryllium. Uh, it does not have the aluminum component. And I threw this in just because I thought it just showed something interesting about this guy. This was an announcement to the American Journal of Science by Bertrand about him turning over a collection. This was a few years before he died, a collection of 14,000 specimens of fossils from all over France and Europe. And uh, what struck me was one of the things that has brought about progress in science is archiving and continued knowledge, even though people come and leave the earth. But the individuals that do this, they have so much attention to detail, and they often are collectors. Dalton was a collector. Dalton sat around too, and from chemistry, he's known, but sat around and um, kept detailed logs of the weather every single day and trying to figure that out. They do all kinds of extra stuff, but it's remarkable that anybody pays attention to the more interesting or useful things they come up with. Uh, so it just was a slice of life in the personality of a scientist, in my thinking, of a 19th century scientist, because we couldn't have gotten here where we are without those people. So fast forward now to the end of the 19th century, you had the discovery of X-rays, sort of by accident, and then uh, while trying to investigate X-rays, uh, Andre Becquerel just threw some uh, darkened photographic plates into a drawer and had some uranium salts in there with the drawer shut in the dark. And then he found those had been exposed. And that's Lincoln's wife's hand. I think that was the first x ray. She had her ring on. And, um, but 1903, up to 1903 here now, three particles for radiation were known. Alpha particles, which are a helium nucleus with atomic weight of 4, two neutrons and 2 protons. And beta particles, which are electrons, um, and you can also have, I guess, positrons, and gamma rays, which had no charge, no magnetic field associated with it. They couldn't be bent, and they were very penetrating. I just thought it interesting to point out that that was subject of Marie Curie's thesis in 1903 for her PhD. One other thing, this pertains to something I'm going to talk about here in a minute. I've, there was a lot of switchboards around when I was a kid. Uh, I liked the switchboard operators when I encountered them because they were always nice to me. And they were almost all women as well. It was back when there was a lot of labor intensive stuff and not being automated yet. And you think of it as this relates to the beginning of information technology. In 1901 in the United States was the breaking point in a way at which this agrarian nation, the United States of America, became split, and half of the people were working in urban industry. And it related to the Industrial Revolution. Germany had similar economic development. Germany had been an agrarian society all the even before it was unified, and it went through an extraordinary transformation in 50 years to become a highly industrialized and productive country. So one of the points I would make, you look at all this stuff they have here built. There's a lot of reuse of stuff, a lot of wear and tear. The stuff gets broken down, and there are relays involved in the function of this switchboard. Relays that have to be able to turn on and off. They're like nodes in a network in an abstract sense. So the Industrial Revolution and development of these technologies, one thing that's I don't hear much spoken about, but the need for durability of equipment is a driving force in research, development, and economy. And the first practical commercial application of beryllium was in arose in the late 1920s, I guess, from little springs and the clappers on relays that get all the slamming repeatedly, that get scored with arcing and electrical burns, and the metal just fatigues and starts to break down. They began to use beryllium copper alloys, even though beryllium's pretty hard to get, right? Pretty one of the things that always fascinated me about, actually right back to when I was a teenager, I wondered about beryllium. Why don't I have any beryllium around I could mess with? You know, I I did a lot of experimentation. So I thought this was an interesting thing. Here, this is a long distance operator trying to give the number of Avogadro. So when you mix a few percent, I think about 2% of oil in that range of beryllium with copper, it enhances its strength markedly. It becomes, beryllium's nice because it's so light. It's an atomic number 4, and copper is really heavier than iron. Iron is 26 in the periodic table, and I guess copper's 29, zinc is 30 in its atomic number, and the atomic weight goes up with the atomic number generally. So it wasn't necessarily as light as the beryllium or even steel or something like titanium could be, but Uh, it was super strong and very durable. And um, it also conducted electricity almost as well as pure copper. Uh, Not quite as well, but one of the things about it, you have properties that are being studied, like hardness. It leads to creation of machines and standards and standard procedures for determining and some measure of a property, like hardness, and how to compare it. And so the take-home message on this slide is copper beryllium has extreme strength. Uh, it's corrosion resistant, and it's non-magnetic. It's non-magnetic, not like iron. So, an interesting thing, I like tools, and I grew up using tools a lot. And yeah, I know I'm a tool user. And so, uh, I also like grinding wheels. I always like sparks, like, like making things happen. Uh, uh, Sparks, what do they happen? You got something made out of steel, you're like putting it on a grinding stone, and the sparks fly, and uh, uh, little bits of the iron or the steel, little particles are being ripped off the uh, metal structure and flying away, and they ignite in the air. And if they have a little bit of carbon, like carbonized iron or carbonized steel, uh, even burns faster. They can get up to very high temperatures very quickly. Uh, Anybody think of any situations where that's not a good thing to have sparks? One of the advantages of copper beryllium, again, I point out there 2% alloys, is a ballpark. It's not exact. It depends on their proprietary differences in that alloys, but it's in that ballpark. Uh, they generate, if they generate any sparks, they're called cold sparks. They're low thermal energy. And in most environments, it's not enough to ignite flammable vapors and gases and dust. And you look at all these 11 tools I put out here, they're all with beryllium copper. The cost of those would run, I estimated, close to $10,000. What do you think of that? Would you rather go buy some cheap junk uh, that'll break and uh, get you in a disaster, or go ahead and spend 10,000 to avoid your plant getting blown up by having non-sparking tools? There's a good reason to use these. There are places where you need this kind of thing, like oil rigs. And if an oil rig goes bad, it's uh, terrible. It can end up like the Deepwater Horizon well, spilling. Now, this was not because of sparking from tools. It was a different thing, but it's just to point out oil rigs are a dangerous place to work. I don't know if you ever, it's like certain kind of people work on those. I've known a few of them. And I didn't really get along with them, but I wouldn't want them to die in an accident. And when you have machines with a lot of power and large structures with non-physiologic physical parameters or conditions, high pressure, and things that are beyond what the human body can take, safety becomes paramount. And here's a picture of these is some Ukrainian coal miners, and one of the problems in coal mines is methane gas accumulation. So if you were working with tools and you had beryllium copper tools, you might be less likely to ignite methane if you hit a pocket of it, or if you have an explosive mixture of methane developing. meaning a combination of oxygen from the air and methane gas. That a little spark would be um, an explosion. And um, chemical plants, uh, such as this one in Texas uh, from 2019. Uh, I'm not saying that non-sparking tools or avoidance of non. I'm sure they were using non-sparking tools when they worked, but something else caused this. But I'm showing the hazards. And one of the points, everything about where we are in science and as a society is uh, thanks to working people. And a lot of these working people, not just in our day and age, but hundreds of years, have lost limbs, lost their lives working to make a living as best they could. And uh, they deserve to be uh, in a safe environment as well as possible and get the compensation for their work that they deserve. So uh, this includes scientists. Scientists die in their work sometimes. Okay, here's another place where a non-magnetic tool like copper beryllium, titanium would work as well, but it's non-magnetic. But and brass, but copper beryllium is the uh, usually the metal of choice if you're working around high magnetic fields. I looked into this. If you had a I think 1 gram piece of metal, uh, a piece of iron, and iron is ferromagnetism, uh, or is very attracted to magnets. Uh, and it was in a 1.5 Tesla field, and you let go of it, it would attain a velocity of about 40 miles an hour. And if you got hit with a small piece of metal going 40 miles an hour, it's going to go into you. Um, so uh, it's really interesting. It also occurred to me maybe one of the reasons, this is just a side thought, one of the reasons you don't hear of somebody going in with armed to the teeth, uh, shooting a lot of people in MRI units is because their weapons would be uh, uh, sucked over to the machine and uh, uh, caught up in the magnetic field. Um, One of the things about X-rays uh, and gamma rays as well, high energy X-rays, mid energy X-rays, particularly barium is nearly transparent to it. That's partly because it's so small. You could also argue, why don't you use lithium or boron? Boron is not as, none of them are as strong as beryllium. And basically, it can hold up to a 1 atmosphere pressure if you are using it as the window for egress of X-ray, um, an X-ray beam from an otherwise shielded X-ray source. When I was a teenager, somebody gave me one of these kinds of tubes. It got disposed of with all my other stuff when I left home, but uh, I had my own X-ray tube. I also had a lot of high-powered transformers, 20,000 volt transformers I like to play with. Uh, so the thing is, this has a little diagram just to show you have a window here at the bottom, this tube window, as they call it here. It's a beryllium window that your useful X-ray beam comes through there. And in a way, the um, generator of X-rays is a particle accelerator. The particles it is accelerating are beta particles or electrons, and you can vary the energy of their collision and deceleration and release of X-rays by varying the potential difference or voltage in the path they're to take toward the cathode. Uh, And I just showed an X-ray there in the lower right-hand corner, typical X-ray. Okay, I want to talk a little bit about the chemistry of beryllium. To me, it's not as interesting as the other things about beryllium, but uh, I just wanted to jog your memories and ask if you remember what a mole is. Well, I got a lot of them in my yard. Saw a big hawk in the middle of the yard the other day trying to dig around to find one. He spent about a half an hour there. Uh, must have been hot on the trail. But uh, they're kind of been maligned. Moles are. People don't want them because they want their yards to look like golf courses, but they eat grubs and things. They don't usually hurt roots, and they aerate the ground. So let's look at the periodic table. The modern periodic table, where the order is based on the number of protons, goes back to Moseley's work. Moseley, who was killed in World War One as a total waste, but in his, I think his doctoral work, figured out how to attribute the identity to and properties of atoms to their proton number. Well, anyway, one thing I always liked about beryllium, it's because of my love of mathematics, it's like a perfect square, 2 by 2. It's in the second row and second column. And just telling you that may help you remember that. The only other element like that is hydrogen, which is in the first row and first column. So, and I would point out the periodic table has 7 rows for 7 periods and 18 columns and an extra outset F block for a whole different kinds of range of orbitals. The beryllium, in the first row, you have the first S orbital. That's all you got there in the first orbital. The second orbital, you have S and P orbitals. As one S, the 2s orbital, as it would be called, could hold 2 electrons, and each of 3 p orbitals can hold 2 electrons. So, in these, especially second and third rows or periods, you get this row of octets that you may recall. But at any rate, beryllium, you got to remember, it's just got, as valence electrons, it's a 2s shell, which has 2 electrons in it, that it's willing to give up quite readily. It ionizes quite easily to +2 ions. And I wanted to just mention important compounds of beryllium. Beryllium oxide is probably at the top, and the various beryllium halides. And I'll let you read this more on your own, but these are important in industry and developing other uses of or products for use of beryllium. Lewis diagrams, like interestingly, the beryllium oxide is a double bond with oxygen. Oxygen is happy; it's able to pretend it's neon, and like it's got it's got 2 inner electrons in the first orbital, and the second orbital gets 8 electrons. It can believe it has when it shares with beryllium. You can have beryllium in combinations with halides, which isn't very surprising, and then ionic salts like beryllium sulfate. At the bottom, I show the sulfate ion, and its Lewis diagram as well, just to sort it out. Interesting, sulfur is in the same group as oxygen, so they're all chummy there. Okay, you remember what a mole is? A mole is the number of atoms in 12 grams of carbon-12, and Avogadro's number symbol often is N sub A. is about 6.02 times 10 to the 23rd particles. And if you get that many atoms of carbon 12, uh, you will have 12 grams of mass. So, looking back at this periodic table for a second, take the atomic number is the average of isotopes. Isotopes are the same atom; they have the same number of protons and varying numbers of neutrons, and they take the ones naturally occurring and the average of by natural occurrence. So I don't have atomic weights on here, but uh, at any rate, if let's say the atomic weight of beryllium is a bit over 4, just slightly over 4, I believe, uh, then 1 mole would have whatever the atomic weight is in grams. It's pretty cool. So, okay, the chemistry's fun. Bertrandite, Bertrandite hydrous beryllium silicate with it has no aluminum specifically in it, but beryllium with silicon and oxygen uh, is the has become a very important source of beryllium. Before I go on, I think we're doing okay on time. I wanted to mention it's only 1932. When 1932 comes around, science circles should celebrate the discovery of the neutron. I pointed out at 1903 there are only 3 forms alpha, beta particles, and gamma rays of radiation were known from radioactive decay. Um, and maybe I shouldn't call alpha particles their emissions, but rather than call them radiation. But those are the what are were coming out of uh, um, radioactive decay of matter. Um, they had known that uh, they bombarded beryllium with alpha particles, and they did this with radioactive sources. Uh, that some kind of beam was generated, and uh, uh, there was confusion for a long time. People seemed to want to believe this was maybe a gamma ray because it didn't respond to magnetic fields or electric fields. And an experiment had been designed where they found that uh, it would produce charged particles from, um, excuse me, from bombarding um, a plate of beryllium, first off, with alpha particles, and then having a secondary layer of paraffin. And after the paraffin, a lot of degradation of the beryllium happens as well as gradually, but as well as the paraffin. And charged particles got that could be detected were produced. So showing this again, you have this polonium-210 source. It's very interesting how Chadwick got his polonium, and I put, I'm pretty sure I put the description of, I did some research. I was wondering where to get that, because these days most of the polonium-210 seems to come from nuclear reactors, and he got it from uh, uh, radium breakdown in cancer treatment places. But that aside, you have polonium-210 as a source, and he actually bonded that to a little bit of copper. And when he uh, so he would make a thin focused film on it as a source of alpha particles from the decay of polonium-210. It's one of those things, if it gets put in your tea, you know, you're out of your native country and you happen to maybe be in London or someplace and somebody puts it in your tea, you'll die within um, probably within a week because the polonium, it polonium is 94 atomic number. It's in the same group as oxygen, and it will end up in your cells and releasing alpha particles in your cells and basically destroying you from inside while your body continues to function until the infrastructure is destroyed. It's a horrible death. Polonium's pretty dangerous. So alpha particles are released, hit our beryllium. This is kind of faint. I hope you can see it well. Beryllium plate, and they know now that they were trying to figure out what happens. Well, neutrons get knocked off of the beryllium. The one reason is beryllium, lots of atoms tend to like to have the same number of protons and neutrons. Beryllium has this kind of extra loose proton in its nucleus, neutron in its nucleus. And so it has uh, atomic weight of 9 something and not 8, as one might expect. And so when it gets hit with an alpha particle, it will fuse pretty readily and degrades the beryllium to carbon, and that extra neutron gets put into motion, probably a slow neutron or thermal neutron. And when it hits the paraffin, it will knock the hydrogen protons that are attached to the wax. Paraffin is hydrocarbon. It's long chain hydrocarbons, and then you have charged particles that you can detect going into the detector in the ionization chamber. Uh, um, I used to have a guy. I have somewhere. I've got a Geiger counter from the old days, actually, but it's more than I want to go into as to how they would detect the charged particles. But you could also detect changes in the charge if you applied uh, a um, uh, a electric field. You could sway the path of the particles, and you could uh, change it with magnetic fields as well. Not quite the same way as with electric fields. But my question to you is, can you think of anything else that's sort of like paraffin that could be uh, hit with neutrons and have all kinds of hydrogen uh, uh, atoms knocked free as proton particles? I'll let you ponder that a moment. I just show a little relaxation slide here, hoping that it's not focused for me yet. There you go. I hope you can see it. Just thought it would be a nice slide to show uh, that relates to kind of shooting neutrons into things that will, so they can disrupt the nuclei that have been present for billions of years and uh, alter them forever. Human beings are, in a way, a metaphor for the paraffin. You see that paraffin there? In the 70s, they started talking about neutron bombs because they wouldn't destroy as much property. They would destroy human beings. So this is an interesting story, and I won't go into great detail about, but it relates to beryllium. Um, there on the right, I think in the sunglasses, is Louis Slotkin, and uh, the Helian is on the left. No, he's just over the guy's left arm who's working on the gadget. This is the um, uh, one of the first atomic bombs. Well, the guy that was behind the bomb that's being assembled is up there at the top. He was working with, I think, tungsten carbide bricks on there's about a 13-pound or 6.5 kilogram core plutonium. And the tungsten carbide was a neutron reflector, and he was building a little wall around it. And the point of it was to try to detect what they could do to bring the plutonium to criticality without actually doing it. And all the sensors and Geiger counters were just flying off rattling away, and so he thought he better bring it down, and he started to disassemble his wall of bricks, and these bricks were quite heavy, and he fumbled and dropped one right on the core uh, of and there was a blue flash, which is because of ionization of air from all the energy that's released, and he got irradiated as this plutonium core approached criticality, and uh, he ended up dying. Uh, just about a year later, Canadian chemist, physicist Louis Slotkin was using beryllium. Beryllium has a remarkable property of being able to reflect and moderate neutrons, and it can also multiply neutrons because it has that beryllium 9 has that extra neutron, 5 neutrons for its 4 protons. So sometimes a neutron, if it hits the nucleus, although the beryllium doesn't have a large cross-sectional absorption of nuclei uh, compared to some things, it um, can split the beryllium atom back into 2 alpha particles and a free neutron, in addition to the neutron that's bounced off it. So it can end up with 1 neutron becoming 2, and destroys the beryllium in the process. But um, a lot of times the beryllium just scatters the neutrons backwards and toward the desired target, which can be a nuclear reactor core. And so Slotin, I'm sorry, I'm saying his name wrong. He was using a screwdriver, which Fermi had advised against, that kind of non-standard tools. And this is something I've seen physics guys do. Physics guys I've known have worked in labs that have bare wires and all kinds of stuff that seem hazardous. He fumbled, and the beryllium dome over the core fell onto it, and it started to go to criticality, and he uh, flipped it off and kind of saved the day, but he died about a week later. So beryllium is useful because of its nuclear properties, but this is dangerous stuff. So we have 12 isotopes, so of beryllium, but there are only 2 that I think are really interesting. Beryllium-9 is the stable one. I'm going to talk about where that comes from. And beryllium-10 is quite interesting. It has a much, much longer half-life than any of the others, 1.38 million years. And it's formed by a process called spallation. About 4 billion years ago, roughly, you had volcanoes spewing nitrogen and carbon dioxide, and we started to develop an atmosphere of carbon dioxide, nitrogen, and water. And so there was an atmosphere developing with carbon, oxygen, and nitrogen. Of course, carbon has atomic number 6, nitrogen 7, and oxygen 8. when cosmic rays from uh, uh, gamma rays or charged particles, depends, hit, uh, come in from outer space, they can cause changes. When, for instance, alpha particles hit uh, uh, carbon, nitrogen, or oxygen, they can produce beryllium-9, and beryllium-10 can also be produced. And the thing that I think is cool about beryllium-10 is it works its way down. It's estimated roughly 2 years, and it's on the surface of the Earth from precipitation or settling or whatever. And it can be used in cosmogenic nuclide dating. Um, this is the same, a different thing from the swipe right things that young people do, but not that kind of dating. But geologists, like some of our folks here, might have used this, and it can date samples older than the 50,000 year limit of radiocarbon dating, and extends the timeline of what we can date back 10 million years. It's tricky. You got to figure out how much you start with, and the amount that's produced. It's produced continually by these atoms in the upper atmosphere being hit with um, uh, the charged particles from outer space, but and it varies with sun activity. So you've got to correlate it with other things to get as accurate an estimate of the age of something as you can. But once it gets out of daylight and covered up, so that it's shielded, it's doing its thing and aging by the according to the half life. I better speed up here. Um, Now there's another thing. Oh, yeah. Well, the triple alpha process. This is quite interesting. 1954, Fred Hoyle predicted a state which came to be known as the Hoyle state. It's an excitation energy, it's a resonance, and the ground states of carbon 12, uh, and it's at a specific energy level, and that's really critical, actually. And he realized if for you to have the amount of carbon 12 that you see in the cosmos now, that there had to be some kind of a process, such as what you see in this diagram, where you can have two alpha particles collide and form beryllium-8, which is super unstable and has a very short half-life. But if like in a sun, as it's starting to use up its hydrogen helium stores, and it's a mature star, and it's pretty large. You can have an alpha particle hit it at the right time in this time window. You can have an entity with the components of 12 neutrons and 12 protons that's in this Hoyle state. Now, 99.96% of the time, it's felt, those atoms that are created this way fracture back into 3 alpha particles. But 0.04% of the time, it settles down and makes carbon 12. And then the carbon 12 can go on to make other things by other nuclear reactions, which can be complicated, but alpha particle capture is a big thing, so they grow by twos often. But at any rate, this is a bottleneck of stellar nucleosynthesis. And I would say that it's hard to imagine carbon that would, availability of carbon in the universe that would lead to anything such as our existence as humans, or living creatures that are carbon based without this process. Now, I realize I'm running close to end of time here. Like John von Neumann defined all the natural numbers based on the empty set, and you could say, well, without the empty set, if that somehow didn't exist, he wouldn't have been able to give a rigorous definition of the natural numbers and the integers. But the empty set's an invention. This this is represents reality, and it's if this were not just right and didn't happen, then we wouldn't have the carbon to have much of anything, and the carbon was a large part of what developed from other elements after this. There was also a paper, I don't know, 1989 maybe from Caltech that talked about this. They did some, might have been 89, this energy level that's so critical. And they said, they modeled it and said, what if it were a little higher or a little lower? And either one would have resulted in a dearth of carbon in the universe. And so it's a sweet spot, this excitation energy that allows this to form stable carbon-12 in sufficient mass quantity that we can enjoy the universe as we do. This is just to show relative abundance of elements. You look at beryllium here, up in like about 2 o'clock on this, it's quite limited. Hydrogen is the most common, and helium next, then carbon-12 and oxygen and these other elements. But all of those that come after helium really require getting through that beryllium-8 bottleneck. And lithium, boron, and beryllium are generally formed by what's called spallation, when the carbon-12, nitrogen, or oxygen atoms are hit with cosmic rays, meaning charged particles. They will break down in certain ways to form beryllium-9. Just to run through, I got just a little bit more. There's we owe a lot to people. Everybody's got a hungry heart, and the prospectors and explorers and even people that don't know squat and can't get along with anybody, that they go out and they dig, and they'll find things. And this is a nodule of that contains beryllium in the form of bertrandite from Spore Mountain, Utah. I've ridden motorcycle near there before, and it's pretty well, pretty arid, and it has, because it's kind of loose volcanic stuff around it, it has to be pit mined, so it does a lot of damage. But it's become and there's comparison here of how bertrandite and beryl extraction is done. And I won't go into that detail, but bertrandite has a tiny, well, it says down ore grade 0.5% beryllium by weight, whereas beryl can have 2 to 4% beryllium by weight. So you would think beryl extraction would be cheaper and easier, but it's a lot more expensive, actually. So they can gather up all this ore, and with mechanization and kind of mass chemical attack and extraction, they can end up having right here in the United States, in Spore Mountain, producing 80% of the beryl of the beryllium in the world. 80%. It's pretty remarkable. This shows where these bertrandite and beryl are found around the world, but that is the Spore Mountain, Utah is the big one. So beryllium has very high heat capacity. It takes a lot of heat to make it change its temperature, and also doesn't tend to change its length so much. So it's great to use for things like um, uh, extreme environments like outer space, and to make the James Webb Telescope mirrors. Beryllium was uh, used, and a surface of gold put on it. Uh, I'm sorry, 18 hexagonal segments. Uh, Beryllium that weighs like 705 kilograms. High purity, lightweight, stiff beryllium, high grade. Uh, it's coated with 700 atoms thick of gold, because silver is the best reflector of all the elements for visible light, but gold is far better um, for uh, um, infrared, which is what the uh, James Webb spaceship. If I can have just like 3 or 4 more minutes, I'll be done. Um, is that okay? Okay, thank you. Uh, we mentioned Materion, or I have mention of it in my slides, from the 1920s, the Brush labs in Cleveland that became, Brush Industries, and then Materion. And Materion is involved in the production of the raw beryllium for these mirror segments. And one reason I wanted to point that out is not because I'm pushing companies or anything, and I think they're in science, technology, and innovation. There is a culture that uh, is required for it to be successful, and it's a composite of academics and private industry in the United States, and they had the know-how from almost 100 years. Um, so now, inflammation, acute inflammation, rubor, calor, dolor, tumor. That's what we used to say in medical school when we first learned about it. Subacute inflammation, it lasts a little longer. Chronic inflammation, you end up with round cells, not neutrophils, infiltrating an area. Like here, where you see all these little blue dots in that center, that's a chronic inflammatory process, uh, characterized especially by macrophages, lymphocytes as well. And they can lead to fibrosis and tissue damage. And I have a few slides, which, because we're kind of pushed the time here, I won't deal with it too much, but just to let you see of inflammatory infiltrates in tissue. And granulomas occur when you get inflammatory cells, like all the um, blue dots in that circle around the center. It tends to wall off an offender. So that's what a granuloma is. Um, well, granulomatous diseases include berylliosis, a lung disease caused by breathing in dust of beryllium metal, and it happens by delayed hypersensitivity. You get exposure and you get sensitized. And some people have genetic disposition towards this that makes them much more susceptible. But most of the time, it relates to inhalation of beryllium fumes or dust. It can also happen with skin exposure. Uh, so it can be very severe. It can lead to pulmonary fibrosis, which means, in my terminology, leather lungs, where your lungs are totally destroyed and don't work as for oxygen exchange. And here's an X-ray of a guy who's 54, chest X-ray. This is in the lower left. That's a normal chest X-ray, just for contrast. But in the upper right is this chest X-ray of a 54-year-old guy who has worked with beryllium. He has berylliosis, but he was working with beryllium, uh, things with beryllium components in aerospace industry and manufacturing. You got any of that stuff, you can't mill it, you can't grind it because you'll create dust and you can end up breathing it in and end up hurting yourself. So, quick thing, you're thinking I don't work in aerospace or work with beryllium, but we're in a new climate, not so good. And we're having wildfires like this. And there was an excellent bit of investigative reporting that I thought, and I have this in my thing, and I encourage you to look at it. There's a little video about it, um, the wildfires in California, and homes are full of beryllium, bits of beryllium. It's not in massive amounts, but uh, uh, in small amounts in lots of components of things, especially electronics. It gets burnt up, it gets in the dust and ash, and you stir that up and you end up breathing it. So wildfires increase the chance of uh, uh, ordinary people in unfortunate situations getting exposed to toxic things like beryllium. And I think that's not going to be the end of it. There's going to be a lot of things like this that are consequent of our neglect of climate crisis. So these are just summary slides on the uh, um, important properties of beryllium that we've talked about, and I'll stop there.